Hello everybody, and a very warm welcome to this ESIstream webinar enabled by Teledyne E2V and in cooperation with the IEEE. My name's Mark Holdaway, and over the next hour or so I'll be your host. In this session I'm hoping to shed light on the whys and wherefores of modern high-speed serial data interfaces, with a particular focus on the open source ESIstream system as created and maintained by Teledyne E2V. By way of introduction to this topic, let's talk about the data transfer challenge. This is a discussion that centres on a choice between adopting a standardised approach or selecting an open source alternative. Both techniques have their proponents and benefits. This is a discussion about data transfer and removing a critical speed limitation in data conversion systems. It's a discussion about adopting either a ready-made standard or considering the alternative, an open source approach where simplicity, minimal resources and power optimization are the priority. One option is a powerful industry standard serial link system proposed for high-end data converter applications and supported by a number of major players in the semiconductor business, namely JEDEC's JESD204 standards. It is no surprise this system receives a lot of industry attention. However, even leading proponents of the standard recognise the complexity of getting their system up and running on complex substrates, evidenced by the sheer depth of comprehensive application notes on the topic. Part of the challenge the standard aims to solve is to provide comprehensive support across many complex use cases and market applications, stretching the technology's ability to cope. Teledyne E2V took a different approach. One espoused by obsessive customers driven towards keeping things simple and minimizing power draw. The result is the open source serial protocol alternative called ESIstream. This seminar aims to open your eyes to the subtle benefits many systems can derive from this alternative and open data interface approach. Ultimately, however, customers are best served by having a choice of approaches to data serialization. In the case of JEDEC, much has already been written, so this webinar exists to help create some counterbalance and improve the information available, specifically addressing ESIstream. As we consider the question, why ESIstream, we really need to consider in general what are the benefits of data serialization. Serializing data, whilst adding encoding overhead at both ends of the link and thus die cost, repays designers in a number of helpful ways. Most notable is a large saving in pins needed for each data lane. The obvious benefit being you do not need to add extra I/O pins as conversion resolutions increase. Balanced differential pair signaling helps keep system noise low, reduces interference products, and limits power required for transmission, assuming, of course, that you have considered the transmission line design approach carefully and focused on matching impedance of those lines. Furthermore, serial pairs help to simplify board-level PC design. Embedding the clock information within the encoded serial data stream helps to mitigate some of the complex timing challenges that occur in modern gigabit per second designs. Another useful aspect specific to ESIstream is the simple and direct relationship between clock and data. JEDEC, to account for the diverse range of data widths and bit mapping it provides, adds the complexity of fractional relationships between clock and data, requiring extra sophistication within the clock management system. That said, data transmission design remains a thorny topic and one that gets worse as data rates increase, turning PC design into an art and ultimately threatening the ubiquity of FR4 PC material as better performance dielectrics are sought in support of multi-decade gigahertz design. This table shows nearly 2 decades of interface technology advancement as data rates try to keep pace with system demands. It starts on the left-hand side with a first-generation serial data technology, low voltage differential signaling or LVDS. This was the first step on a path away from the parallel interfaces used prior to serial. It then progresses into what is now 4 generations of JEDEC specification writing, all the way to its latest iteration, JESD204C, claiming support for up to 32 gigabits per second lane rates. ESIstream, the subject of this discussion, represents the only alternate high-speed data interface option. Even its initial iteration provides optimal serialization features, including support for multi-lane and, critical in many applications, deterministic latency. Determinism is the ability to specifically identify the time relationship between a data sample point and the point in time the data associated with that sample emerges on the interface. Before going any further, let me stop momentarily and introduce the topics for the remainder of this webinar. Covered here are the following items. We'll talk about ESIstream, specifically what is it and what the main benefits and key specifications are of it. We will go into a description of the protocol, including the data scrambling process together with the receive end decode. We'll talk about how to manage multi-lane synchronization. And then we'll look at a practical application of ESIstream, and we'll refer to a high-speed gigahertz bandwidth quad ADC, the EV12AQ600. This is a product that demonstrates deterministic latency and allows for the synchronization of multiple devices. We'll then look at ESIstream as an alternative to JEDEC JESD204. And then we'll raise the covers on Teledyne E2V's new ESIstream IP packages. And finally, we will wrap this seminar up with a discussion of some frequently asked questions. So again, what is ESIstream? Well, essentially, it's a high-speed serial data link. ESIstream is an efficient, high-speed serial data interface protocol using current mode logic transceivers. It's initially focused on 12 and 14-bit data converters that are typically clocked at multiple gigahertz frequencies. And an ESIstream system, just like a JEDEC data serialization system, comprises as a minimum one transmitter and one receiver. And as you can see in the graphic on the right-hand side of this foil, I'm showing an ADC connected to an Fpga or an Fpga to ASIC or Fpga connection. It's a very versatile link technology. So how does open source ESIstream stand out against the JEDEC standards? Primarily, the three high-level benefits enjoyed by ESIstream users as follows. Flexibility. This is a self-contained spec and it's not tied to a specific converter resolution. Furthermore, it can support a wide range of data throughput rates from 500 megabits to greater than 12 gigabits per second. It's a highly efficient data coding technique, but not only that, it's also a very power efficient protocol to implement. And then finally, simplicity. ESIstream is supported by a short 10-page standard document. A standard simplified by not being faced with the complexity of managing complex bit and frame mapping challenges, nor the application layer commitments of the JEDEC specs, as it strives to be all things to all people. It's a complexity that makes even resolving minor debug issues a major headache within the standardized approach of JESD204. Additionally, ESIstream has also received widespread industry approval from a number of expert customers who find its design elegance, the economic benefits of its low overhead approach, combined with low power demands, a real plus. What are the high-level features of ESIstream and what can it do for you? Important in many signal processing applications, such as beam-steered systems, like used with highly agile radar, as well as in comms and electronic countermeasures, is deterministic latency. Deterministic latency ensures that a target system remains on top of the all-important signal phase information within the design. Synchronization is ensured through a unique to ESIstream signal. Unlike with JESD204, ESIstream does not rely on the expense of an additional precision clock. Rather, as we'll see shortly, it uses a relatively slow pulse that can be chained through multiple devices and is retimed at each active component in the chain to enable a mass of converters to operate as if being one ultra-high channel count single device. EasIstream is currently supporting designs up to 12.8 gigabits per second and has been demonstrated to work in a variety of settings, both single board designs and across backplanes. EasIstream, in common with many serial links, ensures DC balance by limiting the maximum allowed running disparity to plus or minus 16. The link protocol includes the ability to monitor system synchronization through the provision of a clock bit. The protocol includes encoding that ensures a minimum number of level transitions to enable clock data recovery, whereby the maximum run length is kept. Now let's take a deeper look at the specifics of the EasIstream protocol. EasIstream uses 14-bit 16-bit encoding, giving it an 87.5% data rate efficiency. In other words, the encoding takes 14 bits of raw data and adds 2 bits of protocol overhead. The overhead comprises a clock bit, which provides a data line monitor of continuous link synchronization. The second bit is the disparity bit, which is used to ensure DC balance being maintained in each data lane. The resulting 16-bit EasIstream frame comprises a scrambled version of the data word combined with the previously mentioned overhead bits. Note that EasIstream scrambling or encoding can usefully be disabled to help ease system debug when needed. Why the need to scramble the raw data signal? Well, this all boils down to an engineering response to the challenges of transmitting data over high-speed links. Broadly speaking, there are 3 key aspects to the scrambling process. The first, it statistically ensures there are a known number of level transitions within the signal to ensure the link remains locked at the receive end of the link. This locking requires that the clock signal be recovered from the receive end data stream. For this, it's important that there is no DC creep or offset that builds up in the link, as that potentially raises the probability of a bit error occurring. And perhaps most helpful beyond that, scrambling can be designed in a way to minimize the spectral signature of multiple links to help keep sensitive conversion systems electrically quiet and thus reduce interference. This block diagram shows a portion of the EasIstream transmit encoding system, which comprises a linear feedback shift register, or LFSR, which generates a pseudo-random binary bit sequence based on a Fibonacci polynomial. Then the 14-bit Prbs is exclusively ORed bit by bit with the 14-bit data frame from the digital converter to create a 14-bit scrambled data word. It turns out that scrambling alone does not automatically eliminate the potential for large running disparities, i.e. a large number of sequential ones or zeros appearing in the serial data. Such disparities directly impact the link quality as they lead to a shift in the common mode voltage on the differential lines. For this reason, a mitigation strategy is needed to deliberately restrict the total running disparity. EasIstream manages this through monitoring 2 specific variables. Firstly, the running disparity, or RD. This is the difference between the number of zeros and ones in a complete data exchange. Secondly, there's the disparity word, or DW, which measures the same difference in ones and zeros, but once per frame. Post-scrambling, this typical EasIstream data frame that we show here comprises 9 zeros and 7 ones. The resultant disparity word has a value of 2, which is the sum of -9 plus 7, giving you that 2. Note this disparity is less than 16, so well within the range of the system that we already set out. By actively monitoring disparity in the EasIstream link system, it becomes possible to adjust the link to eliminate large disparities from accruing. This process uses the very simple mathematical relationship highlighted here to tame disparity. Basically, this relationship says that the running disparity for frame n is the running disparity seen in the previous frame through the link, summed with the disparity word resulting from the current frame n. As previously stated, the running disparity is to be kept less than 16. So provided the running disparity for frame n stays below 16, the disparity bit need not be changed. However, when the running disparity exceeds 16, as shown here, the disparity word is subtracted from the running disparity count. The disparity bit is set to 1, with the result that data is now inverted through a NOT operation, thus reducing the running disparity. This processing step essentially limits the maximum run length to 48 bits. With the additional clock bit overhead, this run length further drops to just 32 bits. So I think my wordy description on the last slide deserves an animation. So in the following diagram, I'm going to show you frame sequences both prior to and post disparity processing. This animation shows 4 separate word frames being transmitted: frame 0, frame 1, frame 2, and frame 3. With a disparity word of -8, the first frame clearly contains 12 zeros and 4 ones. The second frame reverses that bias towards more ones to give us a running disparity of -4. Come the third frame, we have a problem, as this frame has a disparity word of -13. That means we now have a running disparity that stands at -17. This disparity has exceeded the system limit. You may recall we have a plus or minus 16 running disparity limit. This then calls for the disparity bit to be set, signaling that the third frame's data should be inverted so that it will now have a disparity word of value of plus 13. As we see in the lower frame sequence, the new running disparity becomes plus 9, which is well within the running disparity limit of the system. So that's how the disparity processing operation takes place. So far, we've only shown how the protocol manages raw data and uses scrambling to help establish a rugged point-to-point data link. But you may already be wondering just how does ESIstream establish a synchronized link? The next block diagram introduces the frame alignment sequence, or FAS. Frame alignment is achieved by sending a specific 32 frames of data. This sequence is the so-called comma sequence, which starts 0x00FF and 0xFF00 and repeats for a further 30 frames. This sequence is sent immediately after the sync pulse has been asserted. The first upper data stream or timing diagram shown here is the signaling to emerge from the transmitter. In the second data stream, as seen at the received deserializer output, there's a clear 3-bit misalignment, which is corrected by the frame alignment sequence logic, as seen in the third data stream here. The second step towards lane synchronization is called the Prbs alignment sequence, or PAS. Recall earlier that we use a Prbs sequence to encode our transmitted data. Clearly, to be able to make sense of the received data, we need to have the encode key. This encode key is recovered in the Prbs alignment sequence, or PAS. So immediately following the transmission of the frame alignment sequence, the transmitter then sends 32 frames of Prbs values in the data field, which are captured by the receiver and become the encode sequence within the receiver, or more correctly, the decode sequence. After the FAS and PAS have been successfully received, then each link is considered to be synchronized in the system. The Receive Linear Feedback Shift Register module rebuilds the LSFR initialization values from a minimum of 2 Prbs data frames sent by the transmitter. So those are marked here as Prbs 0 and Prbs 1. This data should be the first data immediately after the frame alignment sequence. When frame data is not the comma code, then the receiver knows the next data frames represent the start of the Prbs alignment sequence. The LFSR uses this initialization value to generate the same Prbs values used by the transmit to scramble the data in the first place. Then the decoding module uses these residual values to descramble data, applying bit-to-bit exclusive ORing between aligned data and received values. And you can see this taking place in the decode module. Here I'm highlighting the data that emerges from Prbs 5 to Prbs 31 frames. And immediately after that comes the scrambled data. And you can see that is being correctly received at the bottom of the slide as data 0 and data 1. Just to stress, one should not be surprised to see that the Prbs frames 5 and upwards deliver null frames. Immediately after Prbs frame 31, the first 2 scrambled data frames emerge at the decode module's output, and that's exactly what the protocol is designed to achieve. This next block diagram tries to show how the protocol fits into a typical hardware design within a multiple high-speed multi-lane system, showing the high-level resources required. For each data lane, an encoding block is needed within the transmitter. Likewise, at the receiver end, a separate decode module is required per lane. Finally, there's one further important item at the receiver end of the chain, highlighted in red, which is the output buffer. This buffer is important as there are always uncertainties and variable clock delays in digital systems, and buffering is an established method to help align data edges in those circumstances. Synchronizing multiple lanes requires an elastic receive buffer to account for differing delay times across the decoded data lanes. From the upper timing diagram, you should notice we have a 4-lane system depicted. Lane B is the first to provide output data, while lane D is the last, which in this example occurs approximately 4 frames later. But this is just a typical system. In the lower diagram, the data is loaded continuously into the buffer and held until the aligned data release signal occurs, shown here in green. In this way, lanes can be synchronized across a large multi-channel array of data converters. This is Teledyne E2V's EV12AQ600 ADC. It's a quad 1.6 gigasamples per second ADC, which uses 8 ESIstream output data lanes. Quite unique about this product is the high bandwidth crosspoint switch on the input side of the chip. This enables input signal routing to any of the 4 individual ADC cores. Rather usefully, this crosspoint switch enables interleaving between the cores to improve the flexibility of the converter itself. The crosspoint switch features a 3 dB analog input bandwidth over 7 GHz. As a result of the crosspoint, it can be figured into single, dual, or quad channel operating modes that facilitate sample rates from 1.6 gigasamples up to 6.4 gigasamples for a single channel configuration. This is a device that suits high reliability applications, including space level applications, and it's undergoing total ionizing dose measurements at the moment, and so far has been measured to exceed 90K rad. This device can be configured in a single lane per core output, meaning that the device provides an alternative approach to perform direct L-band down conversion. Furthermore, this approach avoids the use of numerically controlled oscillators, which can be negatively impacted in a space environment as a result of single event upset events. As mentioned earlier, one of the important operating parameters for many data acquisition systems is deterministic latency. In this slide, we see how in the case of the AQ600, this is achieved using the unique sync chaining feature. The slide shows a single converter connected to a signal processing field programmable gate array. This chip generates the sync pulse used to synchronize the converter and the data link. Now let's run through the sync steps specifically. Firstly, the sync pulse is sent from the sync generator and the sync counter starts. Next, the AQ600's transmitter sends a frame synchronization sequence on each lane, then it sends its data. The FPGA's receiver aligns the 16-bit ESIstream frames and initializes its own Prbs to descramble or decode the data sent. A variable data latency can be introduced by the design, for example by placing a FIFO or an elastic buffer in the data path. Equally, process voltage or temperature effects can impact timing delays within the system, which must be corrected for lane synchronization. At the end of the data counter, the aligned data are read deterministically from the buffers. Data buffering compensates for variable latency by waiting for the deterministic read data event driven by the sync counter. And you can see that event highlighted at the bottom of this foil in the timing diagram. To calculate the end of counter value, two steps are required. The first, a training step, uses the sync counter to determine the typical delay between the rising edge of the sync pulse and the all lanes synchronized event. Once established, this delay remains fixed over the lifetime of the system and considerably simplifies system manufacturability by eliminating the need for frequent calibration steps. Secondly, the study must determine the maximum variable latency to be compensated for within a given target system. Single lane synchronization is achieved automatically after a sync event. When all lanes are synchronized, buffer data are read simultaneously and synchronously. In effect, data buffering allows to compensate variable latency, waiting for the deterministic read data event and the end of counter. However, it's mandatory that the receiver and transmit clocks are synchronous to the sync signal. Here's how an FPGA signal processor might be connected to a pair of ESIstream enabled ADCs and maintain synchronization across a multi-channel system. The two ADCs shown here are brought into synchronization using their unique built-in sync chain capability. The FPGA on the right-hand side acts as the sync pulse generator, providing a signal called sync trig to the first ADC in the chain and maintains the sync counter functionality. Sync chaining uses two signal lines, shown here in green, on each ADC, namely the sync trig input and the synco output. What makes this feature so handy is that it is not a new precision system clock, rather it's a relatively slow pulse edge applied to indicate sync. What's particularly special here is that the synco on each device is a retimed version of the sync trig signal, so that as sync migrates through a chain of connected ADCs, any transit time through individual devices is removed. Theoretically, in this way, an infinite number of chain-connected ADCs can be attached to the chain, and they will all be synced to the same sync trig pulse edge. This is a massive benefit where relative input signal phase timing information is a critical performance parameter, such as in beam steering applications, for example. Note that despite all we've said about sync here, the sync chaining is not a mandatory part of an ESIstream serial link, and the protocol is equally at home in a point-to-point communication role, where the sync chain feature need not be used at all. That said, in those systems, it remains important that the sync signal line is length matched relative to the data line transit length. I can imagine by now you're asking, well, does the sync chain actually work? Well, you bet. The chart here shows ADC outputs from two independent sampling channels of two separate but chained ADCs. The green and the black traces are shown here perfectly phase aligned. So it works. So far, we've considered only the physical establishment of an ESIstream length, but it's worth taking a moment to consider what benefits this open source approach gives system designers compared to the JESD204 standard. There's quite a lot of information shown in this table, and I don't intend to go through all of the points in detail. However, there are some noteworthy items, including the simple relationship between clock and data used by ESIstream. Because of the wide range of applications and products JESD204 needs to support, it has to consider operating with fractional clock-data relationships. Then there is the confusion in the spec arising from the frame mapping that really makes it hard for engineers to identify where in a typical data stream to find the most significant and least significant bits. JESD204 debug probing can really stress even the most experienced of engineers. Take a look as well at the typical Fpga resources demanded of ESIstream. Invariably, an ESIstream implementation requires a third to a half of the resources demanded by JEDEC. Mentioned previously, ESIstream is inherently deterministic. Like with all serial interfaces, there is a penalty to be paid in terms of output latency, but the simplicity of ESIstream means those latencies are kept to an absolute minimum. That completes the introduction into the nuts and bolts of ESIstream. But now I want to move on to some of the latest news, and in particular introduce you to the latest ESIstream intellectual property. Depending on your familiarity with ESIstream, you may already be aware that we've offered in the past a 16-bit intellectual property package. This has been available and demonstrated on a Xilinx VC709 evaluation kit and supported up to 6.4 gigabits per second lane rates. However, today we're announcing the imminent availability of brand new 32 and 64-bit IP packages. These packages, aside from boosting supported data widths up to 64 bits, also double lane rates up to 12.8 gigabits per second. This will help reduce Fpga timing constraints by lowering clock frequency. Furthermore, this announcement means we have the support in place for a more diverse range of target Fpgas. The system shown here on the right-hand side shows a quad-channel board-to-board optical interconnect using small form factor plastic optical fibers. Why are we announcing these new IP packages today? Well, the simple answer is our desire is to make selecting ESIstream a natural choice and to remove any friction from the selection process. The IP packages will include all the source code for both ends of the link, so that's transmit and receive. A fully implementable project supporting both Xilinx and Intel Fpgas will be available. Furthermore, the packages include detailed single test bench simulations for both the transmit and receive. In addition, design notes and a user guide to help set up a project are also available. We really want to make the ESIstream discovery process as comprehensive and satisfying as possible. Now looking closer at the support for individual Fpga suppliers. For Xilinx, we cover the Kintex UltraScale KU040 exploiting the KCU105 evaluation kit. This also supports the KU060 for space-level applications. Tools-wise support comes from the Vivado toolset. For those in the Intel camp, there's solid support for the Area 10 GX with an evaluation system from Reflex CES. The tools support is in the shape of a Quartus Prime 18.1 Standard Edition with additional Area 10 libraries and ModelSim. In both cases, tool licenses will be required, however. The pair of images here show two slightly different evaluation environments in action. On the left are Xilinx Vertex evaluation boards connected via a quad small form factor optical fiber connector, facilitating board-to-board connection and achieving 11.3 gigabits per second lane rate. On the right-hand side is a Xilinx UltraScale system making use of the FMC loopback board. Just want to say a quick couple of words about FPGA mezzanine cards, or FMCs. The FMC standard Vita 57.1 describes an electromechanical standard for a high throughput, low overhead data bridge. Mechanically, the FMC comprises either a low or a high pin count connector, comprising either 4x40 or 100x40 pins. The standard FMC today supports data rates up to 10 gigabits per second with adaptive equalized input and output. This is planned to rise to 28 gigabits per second in the Vita 57.4 version of the standard. This last set of images shows an ADC to FPGA connection via the Fpga mezzanine card. On the left-hand side is a Xilinx Fpga, in this case a Vertex 7, which is connected to the AEQ600 quad 12-bit gigasample per second ADC. On the right-hand side, the same ADC is being used, but here connected again via FMC to an Area 10 card. So we're almost at the end of this webinar. Before closing, I'd like to run through the key points we've covered today and to remind you of the value open source ESIstream brings to serial data transmission. Most importantly, ESIstream is open source, and as such it's open to specific modifications and developments by the user community. It features low latency and requires minimal digital resources, giving typically a 2 times benefit when compared to similar JESD204 implementations. Data transmission is inherently deterministic, and as stated previously, this is a huge benefit for customers who have to worry about the phase relationships of the signals they work with. The protocol ensures continuous DC balance. Simplicity extends to the straightforward relationship between clock and data. Unlike JEDEC, there's no need to account for a fractional clock to data relationship, meaning ESIstream does not require additional clock retiming circuitry or phase lock loops. And as such, ESIstream is also an inherently easier job to debug as a result. Finally, the focus of today was to introduce the launch of both 32 and 64-bit ESIstream IB packages in support of Kintex UltraScale FPGAs from Xilinx and Area 10 GX FPGAs from Intel. Hopefully by now I've raised your level of interest in ESIstream, and I think you'll find it helpful to have pointers to additional information available from Teledyne E2V. In particular, I want to make you aware of the ESIstream website, which provides high-level details of the protocol together with specification documents, and will ultimately be the central resource from where to download the IP packages. Next in the list is a technical white paper which was published back in March 2019 in a Teledyne newsletter. The EV12AQ600 is one of a new crop of ADCs that implements an 8-lane ESIstream serial link. A link is embedded on the file to each one of these resources, so you should have no problem finding them. And finally, in the very near future, we will be releasing the IP packages for download. Finally, in the last few minutes before we complete this webinar, I'd like to run through a couple of the frequently asked questions we run into. So we'll look at how does JESD204 and ESIstream compare logic resource-wise? What FPGAs are supported by ESIstream? Are there any data rate limitations to be aware of? And what should you consider with respect to the risks of adopting open source ESIstream? So the first question is, how many logic resources does ESIstream need when compared to JESD204B? Well, in the table here, we highlight the FPGA resources to implement 8 lanes. And in the case of ESIstream, the receiver requires less than 4,000 lookup tables for a 32-bit implementation, and for the transmit about 1,400 lookup tables. That compares in JESD204B to 9,500 lookup tables for the receive and nearly 5,000 for the transmit. So roughly speaking, ESIstream simplifies the logic resources by a factor 2 to 3x. Obviously, with open source approach that we take with ESIstream, the number of lookup tables used can be optimized relative to the specific implementation that you as a customer need. So what about the FPGAs that ESIstream supports? Well, in fact, ESIstream can be implemented on any FPGA that has available high-speed transceivers. That includes the GTH and GTX from Xilinx, the GT and GX at Intel, and the SerDes transceivers available from Microsemi. The transceiver specification determines the data rates that can be achieved in all cases. So the limiting factor is always down to the capability of the transceiver circuits. Okay, penultimate question. Are there any limits in data rate that ESIstream supports? Well, the ESIstream protocol itself is not constrained data rate wise. We demonstrated ESIstream can run at lower data rates such as 3 1/8 gigabits per second and below, even down to 500 megabits per second. Much higher data rates are supported by the latest industrial grade FPGAs from the likes of Xilinx and Intel. And as we've already stated previously, speed limit is determined by the hardware design and, most importantly, the raw transceiver performance. Currently, we've shown ESIstream has been successfully implemented at data rates up to 12.8 gigabits per second on major FPGA platforms. Finally, are there any risks when using ESIstream? Well, ESIstream, as we've seen, has been developed primarily with efficiency, simplicity, and high reliability in mind. And don't lose sight of the fact that Teledyne E2V developed this system in support of its traditional high reliability markets. The reliability and ruggedness of the protocol is ensured by design and has been proven by real implementations. It should be highlighted, however, that for an implementation to work reliability, it's clear that the right transceiver design needs to be used and good hardware design practices must be applied. The benefit of open source means that ESIstream allows users to modify and ruggedize the protocol to their specific needs, which allows the link technology to grow with the developing demands of the customer base. And finally, from the perspective of risk, the link technology has already been proven in multiple harsh, high reliability environments as implemented by Teledyne E2V's customer base. Well, that's pretty much it. We've reached the end of this webinar, but before we go, I would just like to wrap this up by reviewing the key topics that we've discussed thus far. ESIstream, or Efficient Serial Interface, we've described what it is and what it can do. We've looked at how the protocol works, and in particular we've considered how the protocol is applied over multi-lane systems, how synchronization is ensured, and we've talked about how the data is scrambled. In doing so, we've taken a look at an example ESIstream enabled product from Teledyne E2V. This is the EV12AQ600. A quad gigasample per second ADC. We've also introduced the new 32 and 64-bit IP packages designed for the latest industry FPGAs. Hopefully we've answered some of your important frequently asked questions. And finally, we've highlighted the support resources available from Teledyne E2V, most notable of which is the website to be found at www.esistream.com. I've been Mark Holdaway, and it's been my pleasure to guide you through the topic of ESIstream today. Teledyne E2V and the IEEE hope that this session has provided some valuable insights into the subtleties of choosing high-speed data links. Do feel free to contact us for further support, as we're always happy to highlight how ESIstream can ease the data link challenge. Once again, thank you very much, and we wish you a great day.
Okay, Mark, thanks so much for that great presentation, and thanks for going over the most common questions. Now, with that, we're going to wrap things up right there. So, Mark Holdaway, thanks so much for taking the time to be here with all of us today, and we'd like to say a special thank you to all of our audience members for being part of this webinar event. Take care and have yourselves a great rest of your day.